This is Surveying 1, Lecture 17, and in this lecture we are wrapping up electronic distance measurement, so it's part 2. So as I mentioned at the end of the last lecture, I'm going to move in for the next topic in this 2-lecture series into setting up the total station. Now, frankly, there's not a whole lot different here from setting up a theodolite or a total station, because in EDM these are all usually integrated into the same instrument. So it's really important when you're using an EDM, as you might imagine, to level and center properly. I'm not going to talk about these techniques because I've talked about them with total stations. You might want to also, however, when you set it up, unlike when you set up a level, think about where you place the tripod legs if you have a choice. Sometimes you don't because you're going to be shooting in all different directions, but sometimes you do. So this illustration about working room is a good thing to remember, because one of the biggest causes of delays in surveying is because the instrument person tripped over the tripod leg, bumped it, and had to basically reset up on the point, re-backside on some other point, and start the measurement process all over again. So something to just think about as you are setting up the instrument. This isn't always the case, because sometimes you might have a situation where you're measuring an angle where the first point, yes, is indeed over there, but the second one is right here, which means you're going to be sighting in this direction, which means you'll be standing with your feet on either side of the tripod leg over there, and it may be that it's just physically impossible. And this is one of the reasons why surveyors often get used to, every time they move in front, when they're close to a surveying instrument like a total station, and they have finished making observations where they need to move even half a step one way or the other, is to always look down to make sure they know where the tripod legs are, because it's easy to lose track. And that way you get very comfortable with moving around a total station all day, because you sometimes are set up all day without ever tripping over the tripod leg and having to re-level and re-center on the point. Now, let me talk about tribracs just a little bit. I'm not sure if we have discussed this previously with total stations, but there is something about tribracs you should understand. The tribrac is basically the leveling base for the total station. So let me bring a total station here into the picture and just point out something. All I want to say in this is that there is a knob on the tribrac, which is sometimes called the tribrac release, and you're able to turn it, and when you release it, you're able to pick the total station off the tribrac, leaving the tribrac clamped to the tripod. And then when you're ready to put it back in again, you place the instrument there and you turn the lock so it goes the other way. In the school's instrumentation, we generally keep those locks locked, meaning there's a set screw that we can set to prevent that release knob from being turned. Why? Because especially with students, it's really easy to have someone make a mistake where they assume that the tribrac clamp is locked, they make a small adjustment in the instrument, and the instrument falls off. These things are extremely expensive, and you don't want to get a bill for what it would cost to replace or repair it. So it's always good practice to check. And I'm mentioning this because many of you will go out into surveying practice where you will have these clamps, but where they may not be locked with the set screw. And so one of the things you should always get used to doing before you pick up an instrument is you figure out which way the clamp needs to work, and you always turn the clamp to verify that it is indeed locked. And the second thing I like to do, because now I'm finished with my measurements, I'm ready to move the instrument somewhere, is always check to make sure it will not come off. Now, the typical way that we move a total station or an EDM is not on the tripod, but sometimes you just have to make a small adjustment or you need to move it 10 feet. And it's permissible then to move it this way as long as you're holding the instrument more or less vertical. Unlike the transits and levels of olden days, you do not take a tripod with an instrument, either a level or a total station, gather up the legs and simply toss it over your shoulder, as you may have seen Indiana Jones doing. This is not acceptable procedure, and so you should be very aware that both in the school as well as with employers, that they will frown and maybe get you into deeper trouble than a frown for doing that. Now, I have visited most of the instrument manufacturers in the world, except maybe some of the new Chinese ones, although I have visited a few of the Chinese ones as well. And they will all tell you the same thing, that these instruments, their mechanical vertical axis is extremely precise, much more precise than the kinds of axes that are found in transits and the old levels. And so they are not designed to be carried in a horizontal position while clamped to the tripod. You could cause bending of the what's referred to sometimes as the axis or the axle, can cause errors in your measurements. It causes other problems as well that I won't get into, such as damaging the ball bearings on which the instrument rotates. So be very careful about that. It's an etiquette thing you should be very worried about, because it can potentially affect your employment. All right, so let's move on. You now know what a tribrac is and what you need to watch out for. As you get more experienced and you start to do various things, there will be good reason to release the tripod clamp, and we'll talk about some of these in surveying too. And then I'm not going to go through the details, but you probably know that when you're setting up a total station or an EDM or anything with a tribrac, you have 3 leveling screws. So there's 1, there's 2, and there's 3. And what you typically do is set up the instrument so that the level vial, that's the thing with the bubble in it, is first parallel to 2 leveling screws. You level it, then you turn it so that it's now 90 degrees to that original line and level it with the remaining leveling screw, and you go back and forth until you have both centered, and then you go into 180 degrees from those 2 positions to still verify that the bubble is centered. All right, so let's talk about the measurement process. So you set up the EDM and reflector at each end, and you measure the height of the instrument and the reflector. With many of these instrumentation, you can often directly input either into the total station or into your data collector software the height of the instrument, the height of the reflector, so that that is properly being accounted for. You want to always verify the prism constant with every setup, and you want to always verify the parts per million values have been set. And that simply means thinking about, have the atmospheric conditions changed significantly since the last measurement? And now you sight at the center of the target, and when I say center of the target, I mean the center of the prism. So I have here a prism, and I'm rotating it a little bit right and left, and I don't know if you can see what's going on, but as we close up on it, notice, so I'm going to do it more slowly now. If we sight at the target, which means we have these triangles where we place our vertical crosshair, you will notice that if I rotate the prism slightly to the right and left, now I can't simulate this very well because I'm in a studio, but if you do this during labs, you will see that the movement of that star shape, which is in the center of the prism, moves right and left in relation to the straight line connecting the 2 triangles, top and bottom. And that's why we always sight at the triangle or the target and never at the center of the prism. That's a very bad practice. Many surveyors who are out there today didn't grow up with EDM, so never learned this particular technique and actually follow the wrong procedure. So this is your opportunity as a young surveyor to actually teach some of the old dogs some new tricks. And now let me continue and just say that after you sight the center of the prism, of course you push the button, You take the measurement, you record it. But then what you should be doing, because EDM measurement is so simple, is to take at least one more measurement, and a lot of surveyors will do 3 or 5 or something like that and average them. But do it after you've recorded the value so that you can confirm that you have, on subsequent measurements, recorded the correct value, because in this class you'll be using a manual recording of the data, and so you always have to guard against typographical errors of various kinds in transcribing the information from the instrumentation to the field book. All right, so let's talk about some of the errors that come up in making measurements with electronic distance meters. So the obvious ones are lack of care in leveling means that you can have an error in your distances. Lack of care in centering means that you're going to have an error in your distances. And finally, lack of care in pointing at your target can not only cause angle, all of these can cause angle errors, but they will also cause distance errors. Now let's talk about natural errors, and you already have had an earful about this from my previous discussion about ppm. So how well do the temperature and pressure you have used represent those values along the line of sight you're observing? And this is again going back to some basic principles of physics and thermodynamics, and that is why we do not place the thermometer in the sun, on top of your vehicle, and so forth. We always want it in the shade where there's free air circulating so that you get the shade temperature. If you go to a weather station, for example at an airport or something like that, you will notice that all the gauges used for sensing the atmosphere's characteristics are inside a ventilated box. The ventilated box is to make sure there's no heat buildup. Obviously, if you have a vehicle that's closed, and even if your thermometer is in the shade, if your windows are rolled up and it's a sunny day, the temperature is going to be artificially high. So it has to be very well ventilated. In fact, some of these systems will actually have a fan for blowing air through the ventilated box to make sure that the temperature that's being recorded is correct. Another natural error is sometimes what we call heat shimmer, or the correct word would be scintillation. So you're looking at a target in the distance and the object appears to be moving up and down, right and left. Well, this is also causing the light wave that's being sent to the reflector and back to also move in those same patterns that you see the target in the distance moving. And so this generally causes longer distances than would truly exist between the points. So you need to be aware of that particular natural error. One of the ways of getting around it is to wait till things cool down, wait for a cloudy day perhaps, or don't try to make such a long distance. One of the things that can also exacerbate this problem is if you are set up in such a way that your line of sight passes very close to the ground surface. So you have a lot of turbulent air, if it's a sunny day, right there that can cause a scintillation, and simply moving your instrument higher or moving it closer can then eliminate that problem. Same thing, even if you don't have this ground, let's say it's actually flat, but there is a major highway that's blacktop that causes scintillation because you have larger amounts of air being heated over the blacktop and then being essentially causing a mini thermal, which causes that same scintillation. Your range to the target, whether it's a reflector or not, can be affected, but also it can affect the accuracy if you have dust, fog, rain, snow, or even things like waving leaves. So imagine a waving leaf in your line of sight between your EDM and your reflector. Now, if it's a phase resolving EDM, a phase shift EDM, the waving leaf simply causes an interruption of the light beam, and when the leaf goes in the other direction, the measurement continues. So your measurements might take longer, and you might want to repeat them several times rather than whatever number of times you have as your standard when you have an unimpeded line of sight. but you'll be okay. If you have a pulse measuring time of flight instrument, you may be actually getting distance measurements to the leaf. And so you have to be on guard to make sure that your distance is not inaccurate. Now, certain instruments actually allow you to estimate at what distance the target is, and you put that in so that any distances that are way off that estimated distance are simply rejected and not counted. So you have to look at your instrument, you have to look at your instrument manual to figure out how to cope with these situations. And the last thing, which is not really a natural error, is that these instrumentation have very sensitive, light-sensitive diodes. And these diodes can be burned out if you point the instrument at the sun. So make sure that that doesn't happen, because your collector, your telescope, is an excellent collector of the light coming from the sun. It amplifies it in magnitude and will burn out the diodes on your instrumentation, resulting in an expensive repair. And then you have instrumental errors. The most common instrumental error is that you have inside this box, this black box, it's never black, it's yellow or green or whatever, but inside this box is a fictitious point that's supposed to be plumbed up over the point on the ground. But because of aging of the components, or sometimes simply due to vibration or shock, some of the components may have moved, and so the effective measuring point is either back of or in front of where the plumb line passes through the instrument. And there are ways of checking for this. They're outside the scope of this course. We'll talk about this a little bit in Surveying 2. Another instrument error that can come up is that you have prisms where they're basically fairly inexpensive, and so the manufacturers will list a prism constant that's only good to maybe a couple of millimeters. And so one of the ways of getting around that is to do what I call super determination of prism constants on your own. Again, this is out of the scope of this course, but we will talk about it a little bit in Surveying 2. Just be aware that you can actually on your own determine prism constants, maybe down to 1/10 of a millimeter. If you're willing to put the effort into it, it can take quite a while. And again, I just want to point out that this is an instrumental error. Pointing at the center of the prism rather than the target surrounding the prism will cause an instrumental error, which can also be classified as a personal error. All right, so now let's move on to EDM accuracy. How accurate are these EDMs? So the technology has its own contribution to instrumental error. So all EDMs will always have an uncertainty that exists in that measured distance that is independent of the distance being measured. And then there's another part of the uncertainty that is proportional to the distance being measured. And this is all in addition to prism constant errors. So I have a table here because I have, as you see in this headline, I've written plus or minus 5 millimeters plus 5 parts per million. So this is not an uncommon accuracy specification that many manufacturers will use for their EDM. Now you can determine what these values are on your own for the EDM you particularly use, because you might have a 3 plus 3 or a 2 plus 3 or a 3 plus 2 and so on and so forth. So for different distances, and here the author has used 30 meters, 40 meters, 60 meters, 100 meters, and 500 meters, and in parentheses has the equivalent distance in feet, but then has calculated based on this equation what the 5 millimeters is. Well, 5 millimeters is 5 millimeters, so you see it's 5 point something, but you notice as you get to the longer distances, now for this 500 meter shot, it's become 7.5 millimeters. So if you divide the 7.5 millimeters by 500 meters, you'll get a precision ratio of 1 in 67,000. But if you take the 5.15 millimeters and divide it by 30 meters, which is just under 100 feet, it's only 1 in 5,882. And this is why I often tell surveyors, do not use your EDM to make measurements for distances under 100 feet, because more often than not, if you have learned good taping techniques, you can do far better than that. It actually drops down to about 1 in 2,000 at very short distances, such as when you are setting out points, whether it's a stake or an iron pin for a property corner and something like that. So be very aware of this and know how to calculate these. Finally, I should mention that in many states, certainly in the state of Missouri, we have quite a few what are called EDM baselines or EDM calibration baselines. Typically, these are about 4 to 6 points that are spread out at different distances over 1,000 to 2,000 meter distance. And what you do is you set up at every one of these points and measure back and forward to every other point on this baseline. And then generally, unless you want to do it by hand, you can run it through a computer program that does what's called a least squares adjustment. Again, I'm not going to go into the details of what that is. That gives you the best possible estimate for your fixed error and your variable error, just like the manufacturer gives you. But this takes everything in your system into account. So how good your personal errors are, how good you are at controlling your personal errors, as well as things like natural errors, because certainly in a 2,000-foot measurement, a 2,000-meter measurement, you definitely want to be considering ppm. Very good process that unfortunately too many surveyors do not use, but this is one of the ways that you can take your EDM, measure it on a baseline, and if the baseline has been properly maintained, you can actually make a claim in court that your EDM measurements are traceable back to what's called a NIST standard, and NIST is the National Institute for Standards and Technology. They're the federal government successor to what used to be called the Bureau of Weights and Measures. And then kind of wrapping up this whole thing, just a few comments about horizontal distance measurement. With an EDM, you never set the instrument so it reads so that the telescope is horizontal. You have to either sight down or you have to sight up at the prism. But because you're using a total station, you're measuring the angle in the vertical plane. Typically on most instruments, it's the zenith angle. So you're measuring from 0 straight up to 90 on the horizontal. And then when you're looking below the horizontal, you have an angle value that's greater than 90. Some instrumentation, however, reads 0 on the horizontal, and you read +1, 2, 3, 4, 5 as you go up, and -1, 2, 3, 4, 5. So you have to be aware of how your instrumentation is set up. But if you are hand calculating, you can use simple trigonometry, as we did in steel taping, to calculate the horizontal distance. Actually, you can also calculate the vertical distance. Now, on most instrumentation today, this is pre-programmed into the instrument, but it's worth it, especially on longer distances, to simply do the hand calculation yourself and verify that it's doing it properly. I have run into more than one situation where the pre-programmed instrument has a mistake in the coding. Some of these instruments will also have a correction for curvature and refraction, and sometimes you can turn this correction on and off. And the reason for that is mostly because you can use the instrumentation to determine vertical distances, which are more affected by curvature and refraction. But I just want to point out that curvature and refraction, especially if they're very long distances, can affect the horizontal distances as well. And then, as I implied earlier, the great thing about electronic distance measurement is that it's possible to measure lines that you may not be able to physically measure. For example, from A to B, we have a line that passes through a building, or from B to C, a line that runs through a bunch of trees. So you can't direct measure these lines. And one way you can do it is set up your total station here, measure to A, measure to B, measure to C. But in the process of doing it, if you're using a total station, measure these angles. And so knowing the two distances here and the angle alpha, you can now compute distance AB. And this is a very common technique that's used in surveying today. And you need to be very familiar with this technique, and we will spend a lot of time drilling on this particular procedure. And with that, we will conclude this lecture and end up on electronic distance measurement procedures.